Thank you for the introduction, and thank you to the organisers of this event, and welcome to our distinguished visitors from Todai. We're very thrilled to have you here and look forward to setting up new collaborations. A major challenge in environmental management for our generation is that air pollutants have large impacts on regional and global climate change, but in complex ways, involving both warming and cooling mechanisms, as we've been hearing a lot about today. And this creates complex trade-offs and synergies in policy development, and may have even led to the false dichotomy that we can have clean air or a cool planet, but not both. So the most important air pollutants that influence climate are tropospheric ozone and fine mode aerosol particulate matter. We call them the short-lived climate forces. They typically have much shorter atmospheric lifetimes than carbon dioxide, but higher radiative efficiencies. Our ability to evaluate the climate and air quality benefits of mitigation strategies involving the short-lived climate forces is currently seriously limited by a lack of understanding of their coupled interactions with land ecosystems that have, up until now, been rather poorly represented in models. So I'm going to tell you about some very new work today that my group have been doing to try and improve the representation of this interaction and the impacts that it has on climate. That the short-lived climate forces play a major role in anthropogenic climate change is not controversial. And it's depicted, hopefully we can keep on seeing it, in... it's happened before. So it's clearly depicted in the iconic, infamous IPCC bar chart, which we've seen a few times today. And so from a global warming perspective, our best estimate of the net effect of cooling short-lived climate forces is that they are masking the committed greenhouse gas warming through the Industrial Revolution by 50%. That's huge. From a regional temperature change perspective, in the current climatic state at northern hemisphere mid-latitudes, the anthropogenic aerosols are having the same strength impact on surface climate as the long-lived greenhouse gases, so they're not small players. And moving beyond temperature to impacts on hydrologic cycle, the aerosol pollution has larger impacts on regional precipitation patterns than greenhouse gases. So in this sense, we can actually consider that it is the greenhouse gases are masking the aerosol effects on the hydrological cycle. So ultimately, it will be policymakers who are charged with making some of these complex decisions on trade-offs and synergies between air pollution abatement and greenhouse gas mitigation. It's up to us, the scientific community, to provide them with the information in the best possible, most useful format that we can. And up until now, we have been quantifying climate impact in terms of changes of concentrations of atmospheric species, single individual species in the atmosphere. But changes in atmospheric concentration are a symptom, not a cause of the primary drivers of anthropogenic climate change. Those are the emission sectors themselves. So this single species approach is useful if we want to try and understand global climate sensitivity or attribution of historical forcing to human versus natural impacts, but if we want to develop climate policy, it's not particularly useful. There's no information here about the actions that are driving the forcing. Actions affect multiple species, oftentimes with opposing climate effects. So coal burning is the clear example of this, that emits both carbon dioxide and sulfate at the same time. It's also backward-looking. This is our inheritance. There's nothing we can do about this now. We have to learn to live with it. So myself and several other groups around the world have worked on developing an alternative approach that is reorganizing this chart in terms of the real drivers of climate change, the economic sectors. And we also purposefully choose to adopt a forward-looking perspective because it's more relevant for policy. And we argue that this approach allows identification of emissions reduction scenarios that are win, win, win. And by that, I mean they're good for climate in the near term, they're good for climate in the long term, and they're also good for human and ecosystem health. So here is the result from our first global sectoral analysis. The sectors are ordered here in terms of increasing net warming, and the contribution of each chemical species is shown for each sector. These are the results on fairly short timescales, so for the 30-year time horizon. Now, the first thing to notice about this chart is that the sector profiles differ greatly. So it's very important to do this analysis. Secondly, what we can quite clearly see is that just how important the short-lived climate forcer effects are relative to carbon dioxide, at least on these timescales, for all sectors, with maybe one exception, household fossil fuel burning. Sectors at the low end of the spectrum are associated with large emissions of aerosols and their effects on clouds, and sectors at the warmest end of the spectrum are associated with large emissions of ozone and black carbon that act to enhance the greenhouse gas warming. So one thing that has always bothered me about this sectoral analysis and also the single species analysis is that it doesn't properly take into account interactions with land ecosystems. So let me give you a couple of examples. Tropospheric ozone has a strong interaction with terrestrial vegetation. It damages the ability of plants to uptake, to photosynthesize, and therefore to uptake carbon dioxide. And the effect is large enough to represent a warming indirect carbon dioxide forcing. So that needs to be included into these results. Also, all of these sectors change the atmospheric oxidation capacity in some way. They're all associated with a certain NOx emission, and this will have a large impact on a formation of biogenic secondary organic aerosol, which is another climate forcing that would need to be included here. So I have begun to think about how we can include these interactions properly into forcing assessments of tropospheric ozone and aerosols. Now, land ecosystems are the major global source of volatile organic carbon to the atmosphere. So I'm going to talk a lot about BVOCs, biogenic volatile organic carbon. The source from land ecosystems is over a petagram of reactive carbon per year. This is 1% of GPP. It is a factor of 10 larger than anthropogenic VOC emission source per year. So it's order of magnitude larger. And it's of comparable magnitude to net biome production, global net biome production, interestingly. So the plants are giving up this precious assimilated carbon to protect themselves from abiotic and abiotic stresses. The dominant compound emitted is isoprene, to the tune of about half a petagram of carbon per year. Another important class of compounds are monoterpenes. Now, once in the atmosphere, there is complex nonlinear chemical processing. These species have very short atmospheric lifetimes, so they only exist for about half an hour before they begin chain oxidation reactions. And this chemistry can alter the atmospheric distributions of all of the short-lived climate forces. So ozone, methane, and these compounds are direct precursors to the formation of biogenic secondary organic aerosol. In fact, as I will show you later today, because these compounds influence oxidation capacity, they also affect all secondary particles in the atmosphere, including the formation of sulfate and nitrate aerosol. So the actual impact of the BVOC emissions on the short-lived climate forces depends critically on the chemical background state of the atmosphere, especially the amount of NOx. So the effect is dependent upon co-located emissions from anthropogenic sources. So the changes in tropospheric ozone, aerosols, and methane constitutes a forcing which could ultimately feed back and change the rate of emission of the BVOCs. The BVOC emission is also going to be sensitive to land cover and potentially land cover change. And we're going to talk about that today. So in the original modeling paradigm for isoprene, which came out of the air quality community that are more concerned with weather-related timescales, isoprene was mostly sensitive to temperature. So that modeling approach was then used in global change studies with the idea that, oh, we have a warmer future world, there'll be more isoprene. And in a past cold world, that implies less isoprene. Then the plant physiologists informed us that there is a direct interaction between atmospheric carbon dioxide and the rate of isoprene emission, and it's an inverse relationship. We call this the direct CO2 inhibition effect. And global modeling studies revealed that temperature and vegetation productivity impacts are entirely offset by the direct atmospheric CO2 inhibition, which leaves the atmospheric chemistry community with a rather uncomfortable question. Well, is isoprene actually rather boring in chemistry climate interactions? We've made a mistake because it doesn't actually change much in different climate states. No, it does not. It means that land use, land cover change is going to be playing the critical role in determining BVOC emission change in different climatic states. Human activities have modified 30 to 50% of the Earth's land surface through the historical cropland expansion and agricultural activity. I find that number completely staggering. And at the moment, the community assesses the climate impact of this historical cropland expansion essentially as a rivalry between the cooling surface albedo change and the warming CO2 release. It turns out that the forcing for each of those impacts is the same magnitude but opposite in sign. So indeed, now there's no consensus in the scientific community on the sign of the global average surface air temperature change to the historical cropland expansion, to anthropogenic land cover change. Several studies do suggest an overall warming, that the CO2 effect wins out, as this one, which was done using the ECAM model, but many of the EMIC studies actually have the albedo effect winning out overall and a net cooling from anthropogenic land cover change. So the question my group is interested in is how important is this historical land cover change on BVOC emissions of reactive chemical species, and are the impacts large enough to perturb the short-lived climate forces? In which case, do we need to consider the short-lived climate forces in assessments of anthropogenic land cover change, because they're not currently considered? So I'm going to tell you about the development of a global modeling framework to study interactions between land ecosystems, chemistry, and climate. And then we'll use the model to try and answer these three questions. What is the effect of the historical cropland expansion on BVOC emissions and the short-lived climate forces? Can we develop an indirect climate effect of BVOC emissions? And then if I have time, I will talk about an extension of these ideas to understanding climate sensitivity in Earth's deep past, particularly in hot worlds, where the vegetation cover was much more extensive. So here's a schematic of our model framework. It is based on NASA GISS Model E2. I worked on the chemistry development of that model for about a decade, and since coming here, we have implemented an interactive terrestrial biosphere. So essentially, in the canopy biophysics, we have implemented the very well-established Farquhar-Bolberry photosynthesis to mottle conductance equations, which we're solving at the land surface model time step, which is dynamic, 15 minutes or less. And in that canopy biophysics scheme, we have implemented a new biologically realistic isoprene emission model. The isoprene emission is dependent upon the electron transport limited photosynthesis rate and also the internal leaf carbon dioxide concentration. So also noteworthy is that we have a dynamic simulation of CI, of the leaf internal carbon dioxide concentration. So we solve this every land surface model time step. We don't just simply assume that it's 70% of the atmospheric carbon dioxide concentration, which is what most other dynamic vegetation models do. And another unique feature of our model is that the temporal resolution is 30 minutes. So the GCM time step, again, traditional dynamic vegetation models usually have a time step of 1 day, which is not very useful for atmospheric chemistry. So in my group, research scientists are working on the interactions with aerosols and clouds and vegetation and also the ozone damage. I'm going to talk for the rest of today, the time that I have, about the impacts of BVOC, the photosynthesis-dependent BVOC emissions on chemistry-climate interactions. So after a lot of work, our carbon fluxes are consistent with current understanding of the contemporary carbon cycle. We have done an extensive evaluation of the model carbon fluxes, mostly using FluxNet data. We have 9 sites of data for isoprene time-varying sites that we've done a fairly detailed analysis. Model does a very good job of simulating the diurnal average variability. We always catch, even with a free-running climate model, 90% of the variance in the diurnal variability. The main weakness is in simulating the magnitude of the isoprene emission. But we are within a factor of 2 in dry season tropics and in the deciduous biome, which is as good as the super high resolution air quality modeling systems used by the US government. Okay, so because the isoprene emission is dependent on the rate of photosynthesis, it's essentially a certain fraction of photosynthesis, that means that the isoprene emission is sensitive to water availability. And so some brute force sensitivity simulations, we turned off the water stress function in the vegetation biophysics and found a global increase in isoprene emission of 30%. And we also ran the model with potential natural vegetation and found a very large increase in the global isoprene source of 55%. So this is an indicator that anthropogenic land cover change is going to be having a substantial impact on the BVOC emissions. So here we are looking at results from a multiple linear regression regarding the relationship between the model isoprene emission and its key drivers, gross photosynthesis and canopy temperature. On the left side here is the standard default model, and then on the right side we have the results from the simulation turning off the water stress artificially. And the whole reason I'm doing this is to demonstrate that in our biologically realistic isoprene leaf production, the gross photosynthesis rate is dominating over canopy temperature in controlling the isoprene emission variability on all time scales. Okay, so this is very different from the previous original modeling approach for isoprene that was simply dependent on temperature. So what we're finding is that water stress decreases the sensitivity of the isoprene emission variability to canopy temperature. So this is because high temperature conditions are associated with drought. And that actually leads to a reduction in photosynthesis and therefore a reduction in isoprene emissions. So in the original modeling paradigm, that would actually give an increase in isoprene emission. So a corollary is that these original empirical isoprene emission models that do not account for the effects of water stress likely overestimate the sensitivity of the isoprene emission variability to temperature. Of course, we would very much like to be able to examine these relationships between isoprene and the drivers at large scales, but we haven't got any large-scale observations of isoprene emission. What we do have are formaldehyde columns measured from space, and our community believes that variability in the formaldehyde column is a good proxy for surface isoprene emission. So what we have done here is look at the correlation between GPP from a global FluxNet derived data set and the fire-free formaldehyde columns measured from space. There's a lot of information here, and we're still understanding everything that is going on. We can see a strong positive relationship between photosynthesis and isoprene emission over North America in spring and fall, and then the relationship becomes negative, fairly strongly negative, over the United States, particularly the southeastern United States, which is a major emission region for isoprene, in the high summer. And one possible explanation for this is the difference in temperature optimum between photosynthesis and isoprene synthase. So isoprene synthase has a higher optimum. It's about 30 degrees C, whereas photosynthesis temperature optimum is around 25 degrees C. So I've used the model to examine the historical changes in isoprene emission over the last century, and also to isolate the impacts of the key drivers. So those are carbon dioxide, which can affect isoprene through carbon dioxide fertilization, increasing photosynthesis, and also the direct CO2 inhibition effect, anthropogenic land cover change, and also physical climate, which is mostly going to be the effects of temperature and precipitation. So the panels on the left here are the change in gross photosynthesis over the last century. Our model projects about a 15% increase due to the CO2 fertilization effect, and that appears to be consistent across most regions too. And then in the right side here, we're looking at the isoprene emission change, and very interesting. So the isoprene is coupled to photosynthesis. We actually find a 20% or more global decrease in isoprene emission over the century, which is driven by anthropogenic land cover change. So even though photosynthesis increases due to CO2 fertilization in our model, the isoprene emission is decreasing rather substantially due to human land cover change. So here we're looking spatially at the impacts of the different drivers on isoprene emission change in a time slice approach, so between the year 2000 and 1880. And I think it's quite clear that the anthropogenic land cover change is really dominating the global change impacts on isoprene emission. And so here's the key point. If anthropogenic land cover change is the dominant driver of isoprene emission change over the past century, that means that isoprene change is a climate forcing. It's a human-induced climate forcing. It's not a natural feedback in the system, because temperature is actually a very small driver of isoprene change over the past century. So in the chemistry climate modeling community, we're not used to thinking about isoprene as a climate forcing agent. I must say, on the other hand, everyone who writes a paper or a proposal about isoprene always starts off their paper with a comment that isoprene is important because it affects climate. But if one starts to look around, there's actually no quantitative assessment of exactly how much isoprene affects climate and how. So to unlock new ways of thinking about isoprene and climate, I'm showing here the contribution globally of BVOC emissions to the short-lived climate forces in terms of a radiative effect. And the numbers are huge. So that ozone radiative effect is double the anthropogenic ozone radiative forcing since the pre-industrial. So these results demonstrate quite clearly that BVOC emissions globally have a profound influence on tropospheric ozone, methane, and biogenic secondary organic aerosol composition. There are also influences on sulfate and nitrate aerosol because BVOC emissions change atmospheric oxidation capacity. The effect of BVOC emissions on the radiative effects of the short-lived climate forces is different in different climate states. It depends on essentially the NOx background atmosphere. So if we take the difference between these two climate states, the pre-industrial, which is this 1850 atmosphere, is already influenced by human activities. So there's a substantial amount of NOx from deforestation burning and from domestic biofuel burning. But if we take the difference, this will give us a new diagnostic that I'm calling the latent indirect effect on climate of BVOC emissions. So part of that is due to the BVOC emission change, and part of it is due to the change in chemical background atmosphere, which affects the oxidation impacts of the BVOC emissions. So this latent indirect effect is minus 0.1 watt per meter squared. So it's not a trivial amount. It's approximately half the sulfate pre-industrial to present day forcing, and it's a cooling. So because we know that isoprene is affected by human activities and is therefore a climate forcing, we have gone ahead and computed, done idealized perturbation experiments to derive the radiative efficiency in different biomes of BVOC emissions. So I'm showing the results here for the tropical, temperate, and boreal zones. And what's interesting is we find the same response pattern across all biomes. So ozone is the largest impact, with biogenic secondary organic aerosol as the second largest impact, and then methane, except in the boreal, where biogenic secondary organic aerosol has the largest impact. But it's a net positive forcing across all biomes. It's a net positive forcing. And the tropical BVOC emissions have the highest net positive radiative efficiency. And to give you a sense of how important this is, these numbers are a 25% increase in tropical BVOC emissions has the same global warming impact as the entire global aviation sector since the great acceleration of the 1950s. So including the historical CO2 forcing in the aviation impact. So that's not a small effect, and it's very relevant for energy crops in the tropics, oil palm plantations. Here I've converted the radiative efficiencies in each biome to a global warming potential, and it's undeniable that the BVOC emission changes have substantial impacts on regional and global radiative balance, So BVOC emissions are only 1% of GPP. It's a small flux of very reactive carbon, but have disproportionately large impacts on climate through perturbing the short-lived climate forces. It's very encouraging that our results are broadly consistent with previous assessments of GWPs for anthropogenic VOC emissions, which are, of course, emitted in a magnitude of about a factor of 10 lower than BVOC emissions globally. So what happens when we put everything together? So we're looking at the pre-industrial to present-day radiative forcing by short-lived climate forces. There are anthropogenic emission changes, and now we're including the biogenic changes. So here I'm showing that as not including anthropogenic land cover change and including anthropogenic land cover change. The main effect is an implied 30% smaller pre-industrial to present-day ozone radiative forcing. So the main impact is on ozone. The biogenic secondary organic aerosol forcing globally is small, but inclusion of anthropogenic land cover change and the BVOC emission changes, therefore, alters the sign from negative to positive, it may be that the biogenic secondary organic aerosol changes have more of a regional impact. For example, when we include anthropogenic land cover change, we find this large positive biogenic secondary organic aerosol forcing over the eastern United States. So I'm going to finish now with this last slide. In past hot climates, vegetation cover was much more extensive. And so we have looked at dynamic simulations of emissions of BVOCs from terrestrial ecosystems and also wildfire in several past hot climates. So one of them is the Pliocene. So this was 3 million years ago. The Earth was about 2 to 3 degrees warmer than it is today, and it's been difficult to explain several features, structural features of this climate state on the external forcing by CO2 and by changes in surface albedo. So what actually happens in the Pliocene is there's an expansion of the tropical savanna into area that's semi-arid and desert today. And there's also a proliferation of deciduous forest. Deciduous is a very high isoprene emitter, and tropical savanna is extremely fire-prone. So we dynamically simulated the emissions, natural emissions from wildfires and BVOCs, and find substantial implied forcings between the Pliocene and pre-human, pre-industrial atmospheres. So this is largely due actually to the vegetation cover change, which alters the emission magnitude, so we get about 100% increase in biomass burning relative to the pre-human, pre-industrial, and 50% or more increase in BVOC emissions. So we find substantial ozone and carbonaceous aerosol forcings. Now, notice the magnitude of these forcings is very comparable to anthropogenic chemical forcings. They're about the same number. So atmospheric chemistry is not an anthropogenic phenomenon. Chemical forcing of climate is always happening in the Earth system. In a hot world, the atmosphere will always be full of ozone and carbonaceous aerosols from burning and vegetation. So in summary, we have developed the Yale E2 Global Carbon Chemistry Climate Model. It couples vegetation biophysics and atmospheric chemistry at high temporal resolution within a global climate model framework. So prior to now, the global modeling of carbon cycle climate and global modeling of chemistry climate have evolved as entirely separate communities for understandable reasons, but that's no longer appropriate. So this is our first attempt to put everything together. And we find that anthropogenic land cover change implies higher BVOC emissions in the pre-industrial than the present-day world. Up until now, in chemistry climate modeling communities, BVOC emissions were either being held the same in the pre-industrial world or were being assumed to be less because of lower temperatures. And the implication of this is that BVOC emissions for the historical Anthropocene are a climate forcing, a human-induced climate forcing, not a natural feedback in the system. And our results so far, we have a lot of work to do on this project, but the results so far certainly suggest that assessments of anthropogenic land cover change climate impact do need to consider the short-lived climate forces. This is, of course, very relevant in forestry for climate protection strategies, biofuel policy, and energy crops. And also, our results are important for deciding the processes that need to be included in climate models for a potential AR6 assessment. And finally, I will finish up saying that BVOC emissions likely play an important role in the Earth's climate sensitivity. Thank you very much for listening.